Welcome to our first lesson, 001, direct proportion. Direct proportion, that's actually a phrase you're going to see in your electricity book. Like, for example, you'll see this. The resistance of a wire is directly proportional, there it is, to its length. Okay, so what are they telling us here? The resistance of a wire is directly proportional to its length. Well, I'm going to write this out. If two quantities, I'm writing it out, see? If two quantities are directly proportional, Yep, come on, write faster. If two quantities are directly proportional, then changing one quantity, here's the idea, changing one quantity will change the other in the same way. E.g., if you double the length, the resistance will get doubled. That's what I mean by the same way. You double the length, well, the resistance is going to get doubled. Cut the length in half, or maybe use a different fraction. Take 1/3 of the length. Or that's a fancy fraction. Take 1/3 of the length, the resistance will be cut in third. The resistance will be 1/3 of what it was. That's all we need by a direct proportion. Okay, R and L change together, I guess is another way to say it. When they say resistance R is directly proportional to length L, they're saying R and L change together. You double the length, you double the resistance. You double the resistance, you double the length. You triple the length, you triple the resistance. Okay, you get the idea there? So I think if you want to say this really briefly, and I do, let's say this really briefly. Let's use a nice color. A nice color, that's a nice color, and say this really briefly. The ratio of resistance to length will stay the same. The ratio, remember they said resistance is directly proportional to length. The ratio of resistance to length stays the same, or stays constant, or remains constant, or there's all kinds of ways you could say it, right? Put it in your own words is always the best way to do it. But the ratio of resistance to length will stay constant. So here's how we use that in a real actual problem here. We have a 500-foot length of wire we do, and this wire has a resistance of 12 ohms. That, I want another color, that is a ratio. It's a ratio of length to resistance. The ratio is 500 foot to 12 ohms. Sometimes we call that a rate. You can call it a ratio. But this ratio is going to be the same, 500 foot to 12 ohms. That ratio stays the same, which means that if we go grabbing a different piece of wire, one that's only 50 foot long, then we can figure out how many ohms it'll have. Notice that what I'm saying is, the ratio of feet over ohms is the same in both cases. Feet over ohms, feet over ohms, feet over ohms stays the same. Hence the equal sign to say stays the same. So what they told us was that this 500-foot wire had a 12 ohm resistance, so that's the ratio of feet to ohms for that wire. Well, it has to be the same. I mean, I'm assuming it's the same material and all that. But if you change the length, it's going to change the ohms, but the ratio has to stay the same. Those two ratios have to stay the same. And I'm going to show you, I'm going to show you a cool way to solve that. And it's called the rule of three. It's a rule that comes from the 1800s, but you know what? It's perfect for these calculator days. If you got a calculator on you, then you don't have to write much. You just say, okay, I got two numbers there. Multiply them. 12 multiplies the 50. And then you divide by that leftover number, 500. Ain't that nice? Slickety-dickety. Slickety-dickety. Slickety-wow. That's cool. So if you go 12 times 50 and divide by 500 on your calculator real quick, you will get 1.2 ohms. So the idea of the rule of three is that you have basically two diagonals here, right? One of the diagonals is going to have an X on it. Yeah, go to the other diagonal. don't do the one with the X on it. Go to the other diagonal and multiply those two numbers together. So two numbers share a diagonal. You multiply those together, divide by the other number, and that's your X. I'll just show this once maybe, but I'm sure a lot of you have heard the old cross products are equal. So let's just take a moment to, what would happen if we did this by cross products? We'd probably say 500 times X on this diagonal is the same as 12 times 50 on this diagonal. So if you multiply the 12 times the 50, you get 600. And then here, to get X by itself, you would divide both sides by 500. You would get 600 over 500, which is, guess what, 1.2. Now, you're paying your tuition. So if you want to do it this way, feel free. It's not going to bother me in the least, you know. But don't you admit that's kind of cool? That's just cool. You're going to want to do it that way, right? Right. Okay. So let me get this out of here because I don't want it anymore. Get out of there. Get out of there. Scram. Come on, eraser. Okay. Because there's something else I wanted to write here. So let's go back to that purplish, pinkish, whatever you call it-ish color. I'm going to say reading number 1. And by reading, I mean reading the proportion. Let's get those out of there at the bottom. Okay, we're reading the proportion. One way to read it is exactly what I've said already. The ratio of feet to ohms is same in both cases, however you want to say it. And then you can use the rule of 3 and all that to solve it. Here's reading number 2, another way to look at the proportion, which is just as valid, and sometimes it's easier to do it this way. I was going to say feet ratio, but I'm going to say the length ratio is the same as, I'm going to say ohms ratio because it's easier than saying resistance ratio. The length ratio is the same as the ohms ratio. Here's the length ratio. See? 500 to 50, that's a 10 to 1 length ratio right there. Well, guess what? 12 to, this ended up being 1.2. And notice that's also a 10 to 1 length ratio. So you could actually read it kind of sideways. So I was saying that, boy, I love being able to erase like this. I was saying that, you know, the ratio of feet to ohms is the same. And it is. You could also say the ratio of feet is the same as the ratio to ohms. You could say it that way. And practically speaking, that means you can kind of take a look at this and say, well, how would I take 500 and turn it into a 50? I would divide by 10, right? Well, to take 12 and divide it by 10, you will get the 1.2 answer. So you actually have different approaches on how to solve your proportion. Anywho, why would I erase that? Anywho, that's the basic idea. Now I want to do a problem that's kind of the same as far as mathematically, but it's also kind of a neat trick. It's something you might even use someday. You got a big old spool of wire, and I'm talking big, not some little spool, but you got a spool that's so big you really don't want to have to unwind it to figure out how much wire is on it. Okay, so you got this big spool of wire. Now usually they got a little, you know, the wire starts there, and big spool of wire. And you want to know how much wire is on that spool, how many feet are left. Well, what you can do is you can just kind of take your cutters or whatever, cut off a length of that wire. Let's say you cut off a 50-foot length, and you measure the resistance of that 50-foot length. Okay, and let's say that you got that the 50-foot length of wire had a resistance of 2.3 ohms. Now remember what your electricity textbook tells you. It says that length and resistance are directly proportional. The ratio of feet to ohms has to be the same for this wire as it is for the whole spool. Well, how do you measure the resistance for the whole spool? Well, that's where you grab this little thing right there, right? That you grab this and you measure the resistance by putting your resistance meter or whatever between here and here, and you can actually measure the resistance of all of that wire. And so it's saying here, imagine that you did that and you got the whole spool has a resistance of 1700 ohms. Now, keep your ratios the same, and they have to sound the same too. Feet over ohms, feet over ohms. It has to be the same in that way. So where's the ohms go? The ohms actually goes down here, right? That's a lousy looking ohm symbol. There we go. Some people like to say, oh, line up your units. Ohms across from ohms, feet across from feet. And Well, I used to say that a lot. It's a good thing to say. Or the other way to look at it is to say, look, this is feet over ohms ratio. This should be a feet over ohms ratio. It should sound the same when you say it, kind of like repeating the refrain of a song or something. Anyway, the point is we don't know how many feet, so I'm going to put a nice X there. I'm going to do my rule of 3, which says go to the diagonal that has 2 numbers, that one. Multiply those two out, 50. And of course I'm just pushing buttons really. 50 times 1700, and then divide by your left number over number, which is a 2.3. And I did solve this, right? And I got something like 36,956-ish feet. Or thereabouts. I mean, if you wanted to know for sure exactly how many feet, you'd have to make sure you measured your ohms like exactly, and the length over here, 50 feet, would have to be exactly. I mean, if you want to be exactly, you'd have to do it that way. What did I just do? You go away. You stay. Okay. So that's a nice trick, right? It's the old how much wire is on the spool trick. You might even use that someday. Looking elsewhere in your electricity textbook, you'll see this directly proportional phrase show up again. Here it is again. The voltage in a transformer is directly proportional to the number of turns. Okay, well, what you know when you see the phrase directly proportional is that voltage to turns is going to stay constant. Voltage to turns is going to be the same ratio. So maybe what we should start with is, what the heck is a transformer, right? Let's start with that. That's a good idea. What the heck is a transformer? A transformer, roughly speaking, looks something like this. You need to make like a little donut of like iron, some kind of iron donut. And then on this over here, you wrap a bunch of wire around it like this. And then on this side, you wrap a bunch of wire around it on this. Okay, one of these sides you call the primary side, and the other side you call the secondary side. Now, one reason you use a transformer is, notice that the wires themselves are not connected, right? Here's some wires, and there's a circuit over there. Here's some wires, and there's a circuit over there, and there's no wires here. So sometimes they call it an isolation transformer. So sometimes you have a transformer just because you want to make sure that if you know, this side of the circuit has a massive surge of some kind, it's hopefully not going to completely destroy this side too. Although I'm starting to wonder, like, does that always work? Anyway, let's not digress so much. So there's a magnetic thing is what goes on, that depending how many turns you have, the voltage is going to be different. You'll have a voltage on the primary side. The voltage is measured basically across these two wires. And then you'll have a voltage on the secondary side. Again, you measure the voltage across these two wires. And these voltages are going to be different if you have a different number of turns. If the number of turns is the same on both sides, you'll have the same voltage on both sides. But if you have like a different number of turns, you'll have different voltages. Now, when they say directly proportional, they're saying if you have twice as many turns, the voltage will be twice as high. Get it? Directly proportional means the two quantities change in the same way. If you have half as many turns, the voltage will be half, and so on. So that's what it means. Okay, so it's good to know about transformers, right? They got primary sides, they got secondary sides. Okay, let's get back to the problem here. The voltage in a transformer is directly proportional to the number of turns. Got it. If the primary side, okay, and that's the thing, you've got two sides. You've got a primary side and a secondary side. So you're comparing the two sides. The primary side has 14 volts. What is the voltage across the secondary side? Okay, now the voltage is directly proportional to the number of turns, means you're going to put volts over turns. So I got to put the number of turns here. Now, how do I use the 4-to-1 turns ratio? Well, let me scroll back for a minute. Remember when I was saying up here that you can kind of look at these things sideways? So the feet are going from 500 to 50. The ohms are going from 12 to X. Okay, I'm going to do that here. The turns, it's a 4-to-1 turn ratio, means the turns are going from 4 to 1. So I put the turns ratio here. Turns ratio. And up here, this is the voltage ratio, I guess you'd call it. What else could you call it? Voltage ratio. So what stays the same is the primary side, you have a certain voltage, And on the secondary side, you have a certain voltage. On the primary side, you have a certain number of turns. On the secondary side, you have a certain number of turns. Now, it's 4 to 1 doesn't mean that it's 4 turns and 1 turn. For one thing, it could be 40 turns and 10 turns. That's also a 4. It could be 4,000 turns on this side, 1,000 turns. Doesn't matter what the actual number of turns is. What matters is the ratio. So we only have to put the ratio in our equation. So anyway, there we are. Notice it's all set up. We can solve that. On the one diagonal, I got 14 times 1 divided by 4. That's going to be 3.5 volts. So our voltage goes down. Now, it's a good idea. Give yourself a little reality check real quick, right? What's the understanding behind direct proportions? It's that they change in the same way, right? So if the voltage goes up, then the turns will go up. If the voltage goes down, the turns will go down, and it works the other way too. We had the turns go down from 4 to 1. So the voltage should go down from 14 to, yeah, that's about right. Basically, divide it by 4, divide it by 4, right? This is another way you could look at this. Divide by 4, divide by 4. It's another way you could have solved the problem. 4 divided by 4 is 1. 14 divided by 4 is 3.5. So I'm throwing these multiple angles at you. Hopefully one of them will stick, but actually hopefully all of them you'll say, oh man, look at all these different things. And that's always to be preferred, because if you know things more than one way, it's a lot easier. If you start to forget, you have more ways to bring it back. Anyway, let's do one more of these things. We've got a series circuit. Okay, what's a series circuit? A series circuit is this. Well, actually, the whole thing is a series circuit, really. These resistors are connected in series. These are called resistors, and that's like a battery, and that's a 12-volt battery. But what I'm trying to say here is series means one after the other. So the two resistors are one after the other. You'd say the two resistors are in series. The whole circuit is just one thing after the other, and so it's a series circuit. There's no branches going off like this or anything. That's not a series circuit anymore. But we don't have any of that stuff. So it's a nice series circuit. Okay, cool. In a series circuit, or even just in a series arrangement of resistors, the voltage across a resistor is directly proportional to its resistance. There's that phrase again. Voltage across a resistor, directly proportional to its resistance. Brace yourself. Okay. So you measure voltage across something. That's the first concept to keep in mind. If you want to measure the voltage across the resistor, you have to take one lead of your voltmeter and put it on this side, take the other lead of your voltmeter, put it on the other side, because voltage is kind of like pressure. And what we're really interested in is the pressure change, how much does the pressure drop when you're going through the resistor. That's what we really care about. So anyway, you'd measure the voltage across that resistor this way, you'd measure the voltage across this resistor this way. I guess I'll call this my R sub 2, and I'll call this my R sub 1. Okay, so again, back to here. Voltage directly proportional to resistance means the voltage to ohms ratio stays constant. Ratios, you can write them like fractions. So the voltage across this one divided by its resistance, which I might as well put 50 ohms, is going to be the same as the voltage across this resistor over its resistance, which is 100 ohms. So that's what they're saying. That's exactly what they're saying. Okay. Now, we got a slight problem if you were hoping to solve it, because, you got two things to solve for. How are you supposed to solve for two things with one equation? Well, you can't. You can't. So what's our breakthrough moment? Our breakthrough moment is to realize that if you measured the voltage across both resistors, it would have to be the same as the 12 volts, because that's what you're doing here. You're putting 12 volts on your circuit. So it would be the same as having 12 volts, and then the total ohms here is 50 plus 100 is 150 ohms. That's your breakthrough moment. So this is, what do you want to call it, E total or something? So the total, which is 12 volts. So the total is 12 volts. The total resistance is 100 plus 50 is 150. And so here, look at this. You can solve that one, right? You can say, well, if the voltage is 12 and the resistance is 150, that 12 to 150 ratio has to be the same, so the E2 to 100 must be the same, and bada bing, bada boom, you just kind of, do the rule of 3 again. So 12 times 100 this way, and then divide by the 150 on that diagonal, you'll end up with, I do believe this ends up being exactly 8 volts across E2. And then if you want, you can do the same thing over here. You can say, well, E1 over 50 has to be the same as 12 volts over 150. And if you solve that one, rule of 3, 12 times 50 divided by 150, you're going to get exactly 4 volts. That's supposed to be a V. 4 volts. And of course you get 4 volts because these are supposed to add up to 12 volts. Remember, it's 12 volts for the whole thing. So if you got 8 volts there, you must have 4 volts there. That's the way series circuits work. Epilogue. So what am I doing on this page? Well, I just wanted to point out some cool things about proportions. Like you see that thing there? That's a proportion, right? What is it? What would you say that is? Well, I'll tell you what I think it is. A proportion is a little equation like that one. It's a little equation that says the two fractions, because those are fractions, right? But fractions or ratios or rates, there's different words you can use. The idea is you got one number over the other, but they're equal. That's what it is. So dig. I got 6 things to dig. One thing you can dig. Both sides in this particular proportion, notice both sides, if you reduce those fractions, you get the same thing. So both sides reduce to 1/2, right? That's a 1/2. So if you reduce 3/6, you get 1/2. If you reduce 9/18, you get 1/2. So they both reduce to the same thing. That's kind of cool. 2. If you convert to decimals, remember how to convert a fraction to a decimal? You basically take 3 divided by 6. That's how you convert that to a decimal. 3 divided by 6. And 3 divided by 6 is 0.5. Now if you come over here and you take 9 and divide it by 18, your calculator is going to tell you exactly the same thing, 0.5. In other words, if you make decimals out of them, they're going to be the same. So that's pretty cool, right? A third diggable thing is the old stretch factor. I call it a stretch factor. Across the top is same across the bottom. And we've kind of seen this already. What I'm saying is, if you wanted to turn a 3 into a 9, you'd stretch it by multiplying by 3. Well, if you multiply this by 3, 6 times 3 is 18. That's what I mean by a stretch factor. The stretch factor is the same going across the top and the bottom. By the way, you can do it this way. 3 times 2 is 6. 9 times 2 is 18. So you can say the stretch factor's going up and down. See, down the left is same as down the right. So they're very rigid things. I don't know what you want to call them. It's like the 3 to the 9 is times 3. That's times 3. If you divide 6 in half, you get 3. If you divide 18 in half, you get 9. I mean, it's like what you do one way, it works the same for the other pair, and so on. Of course, the fifth thing is we could say the cross products are equal. And we can see that again by just going, well, what is 6 times 9? 6 times 9 is 54. What is 3 times 18? Well, it turns out it's 54. So the cross products are always equal. And so we've got, if you look at it, we've got 3 different ways, 3 of them, 3 ways to solve for a missing number. And that's what solving a proportion is really all about. So, you know, if somebody were to write 3 over 6 equals x over 18, well, you could say, well, 6 times 3 is 18. Therefore, 3 times 3, I get 9. Or you could say, hey, if I divide the 6 in half, I get 3. So I'll cut the 18 in half and get 9. Or you could say 6x equals 3 times 18, and you'll end up with the same thing, of course. Or you could do the calculator way. 3 times 18 divided by 6 is boom. Okay, so anyway, that's all cross-producty stuff. And number 6. Wrong color. Number 6. Okay. These are the cinder blocks of math. I love proportions. Cinder blocks of math. First of all, they look like cinder blocks, don't they? It's a nice rectangle, right? It's like a cinder block. But it's also, it's one of those things like, see, I grew up in the days before buttons, before you could push any buttons. So, you know, you had to like learn your times tables. And then the big thing you had to do was you had to be good at setting up and solving proportions. In the 1800s, this is what you needed to graduate. You needed to be good at solving proportions. That's where rule of 3 comes from. It's a phrase from the 1800s. That was it. And the good thing about these is there's a certain rhythm to them. Once you get used to it, it's like riding a bike. You are not going to forget. And so even into my master's degree, for crying out loud, I would often, because I was so well trained in proportions, I would often fall back on a proportion if I ever wanted to make sure about something. It's like, I think this is right. Well, how can I convince myself? I would set up a proportion and say, yep, that's right. So whether I was doing a unit conversion or, you know, something fancy, they're good. They're good for you. So I just wanted to throw that out there and say, yeah, I like proportions, man. So every now and then in the course, you might see me fall back on a proportion to explain something. So hopefully that'll work for you. It's worth spending some time on these to make sure you are 100% that I could wake you up in the middle of the night, ask you a proportion problem, and you go, bleh, bleh, and you'd have it right. That would be good. That's what I'm hoping for here. But of course, the big thing about this lesson is now you know how to interpret this phrase when you see it in your book. What? They're directly proportional? Oh, that just means I can set up a proportion. The things vary in the same way. Doubling this is doubling that, and so on and so on. Having this is having that, and so on and so on. Okay, that's lecture 1. Go get your homework. See you in class.